Okay, in 1 minute we will be having our next host, and he will be talking about embedded-friendly C++ features that makes a difference. Andreas Fertig. Andreas is C++ expert and training, running the trainings around the world with a series of very engaging descriptions of the standardization and new features in the language. He shares insight on writing cleaner, more efficient C++ code and on international conferences. Round of applause for Andreas. The stage is yours.
Thank you very much, Magdalena. Hello and welcome, Code Dive. I think the only thing essentially I can say in Polish, and I'm not sure if it's really right, is something like dobra and dzień dobry. So, thank you. Yeah, today's topic is embedded-friendly C++ features that make a difference. So a few on what C++ did for people developing embedded software, right? And well, Magdalena already did a great job introducing me. Here is my go-to slide. So you might know me as the creator of C++ Insights. I'm also hosting a YouTube channel with the same name, presenting videos, well, you guess it, around C++. I'm author of several books. I write blog posts. So this is basically more or less the free content. If you want to learn with me, I'm available for in-house classes, on-site or remote, whatever suits you best. And if you want to learn as an individual with me, you can check out one of my self-study courses. You can start them at any time, and they should be for your convenience. Magdalena also did a great job pronouncing my last name. I'm German, so my last name, incidentally, is a very frequent German word. It's an adjective, and I'm mispronouncing it for years now, because in proper German it's Fertig. But due to my dialect, I put a hard K at the end, so I always say Fertig, so perfect. You can translate it to finished, ready, complete, or completed, which leaves room for a lot of jokes, because if I say I'm fertig with my presentation, you never know whether I mean I completed it, so I'm ready to give it, or I'm completed with the presentation. So the better part for you now at this moment would be I'm saying that I'm fertig with the presentation and I'm now ready to give it, right? Other than telling you, well, nice that we saw each other for 3 minutes or so. So enough German. As I said, it's about C++ features, and what the C++ standard did, we are going up to C++ 23. And I wanted to tell you more like a story today than just showing you random examples. So the idea is we're talking about an embedded system, something very smallish, so it's a kind of light bulb controlling system, right? I mean, the lights we have in here, nobody really runs around anymore and controls the switches. We do that via software. So it's some kind of smallish embedded system we are having here. And these are the data structures, most of them that you will see during this presentation. Since the light bulb is a somehow network device, it comes with a MAC address. So that's the address, if you don't know that, of your network interface card. Usually comes with 6 bytes. It's supposed to be universally unique. If your device violates that, and if you have 2 devices with the same MAC address in your network, you have a lot of fun figuring that one out. So my first structure here in A is my MAC address structure. I simply wrap my own struct around a std array of unsigned char of size 6. So I have my own data type for that, and it's a little more type safe. The next thing is, since we're talking about light bulbs, the lights here and at home, potentially you might have something similar. They can give you different lights in RGB colors or whatever you call it. So I will use RGB. And if you're setting RGB colors, one way to do it is to say each value of them has a range from 0.0 to 1.0. So floating point numbers. Yay for embedded systems, right? I mean, nowadays we have floating point units, but floating point numbers are rounding numbers, so they're always fun. And we know some property if we are talking about RGB numbers and the range from 0.0 to 1.0. It's only a fraction of what a real floating point number a 32-bit IEEE 754 number can really represent. So we only need a small fraction. And since we're on an embedded device, we don't want to waste too much memory. So what we are doing is we have our own floating point type, an FP16. And for network communication, we have this struct here, FP16, which internally stores a uint16T, because 16 bits are fairly enough for our use case here. We use this FP16 to wrap it in an RGB color struct, so that one comes with 4 FP16 values RGB and the alpha level for transparency if we want that. And now comes the awesome protocol, because I want to keep things simple. My protocol here, I mean, it's an enum, a class enum based on an uint8T. It comes with exactly one option to do in the protocol, and that's update. Nobody knows how to send this update or anything else, but that's not that important for the talk. The only message we are looking at today is the light bulb control message. It contains a MAC address, an RGB color, and a brightness level. So this is what we have as data structures in our system. Now down in F, I present you a type trait that actually came in with C++ 17, so that has nothing to do with C++ 20 or 23, but it still helps in embedded systems, because I wanted to send out this data structure via network. And for all of you who've already done that, most of the cases, I think really all the cases I know, we send data across different CPUs, different architectures if we talking network. So we never know whether the other side is a 8-bit, 16-bit, 32-bit, 64-bit architecture, whether they're running little or big endian. So one thing that's really crucial if you send out structures in a C or C++ sense via the network, we must make sure that there is no padding introduced, because once you're looking at padding, the other side might interpret it differently and you're not reading the actual bytes you want, or off by 1 errors, whatever. This type trait here in F has unique object representation. That one checks, among other things, that there is no padding in this struct. So for all the data structures you want to actually to use being sent out via the network, you can guard them with a static assert in this type trait that nobody, even at a later stage, I mean, you now check it and you are sure, but things are changing. But with that, you can make sure that even if things change and the rules should be violated, people get their feedback, and you still have no issues debugging errors that should not be there. Now the next thing we have is our light bulb class. So that's a small wrapper around a RGB color and the brightness level. So this represents my bulb. It comes with a constructor. Guess what? Takes an RGB color and the brightness level. And because these things might change outside from the constructor simply defers to a function called update. And update then internally will set the color and the brightness level. Imagine that I might be running some checks before and after, and maybe some other actions which are not that important for this talk. The important thing is that this update function can run at runtime, so that would be the usual thing, right? Because you're getting new information during runtime, you want to change values. And now, we might not say that, but a lot of the embedded systems, at least I saw, they use some logging mechanisms. Sometimes it's printf, but we want to somehow trace the state where our embedded system is. I didn't use logging to keep it simple, because what I want to show you is here in B, the new option you have in C++ 23, which builds up on what C++ 20 introduced with std format. We now have in C++ a std print line, as Java had years ago. So yay, C++, right? We are catching up, slowly but steadily. The syntax there is, I think, the same as at least for Python and C#. You provide your format string, and you have the curly braces, which fills in the blanks. The nice thing here is std println is the perfect combination between a printf and cout. For the printf, you have the format string, so you know what you're printing out, but you don't have the type safety. If you mess the format string with the actual parameters, then the output gets real fancy. print line here, it also has, aside from the format string, the capabilities of IO streams. So it checks what data type you're passing as the second and third parameter and does the formatting accordingly. So you should be safe there. The issue here now is, I mean, the good part is my format string and my output here should be safe. But what I want to do here is I want to have a const_expr constructor because this data structure can be perfectly created at compile time. I know all the values. The issue is I have to update it during runtime because otherwise I would have a constant light bulb, which might be a good thing, but not for all the use cases. So my constructor here is actually const_expr. So is my update function. But in this update function, I have this print line, which obviously is something that's more a runtime property. We can argue that the compiler could also emit messages, but we are not there yet. Before C++20, there was no way to have this construct here. You would have to go for a second update function, a runtime, and a compile time version. The code I'm showing here now is based on C++23 because I think this is the cleanest one. In C++23, you got a new if, and this is the if const eval. As you can see, it doesn't come with any parentheses. It does not take a condition because the condition is mangled in the name. The question here is, are we evaluated at compile time or at runtime? The only thing you can do is you can negate this condition as I did it here. So I can say if not, or if you prefer the bang operator, do that. You can say if not const eval, then do that. And this is a hard compile time switch. So if we are evaluated at compile time with this function, my print line and everything that would be in there as well goes away. If we get evaluated at runtime, all that stays in. So you basically have a function where you can plank out things based on whether you're evaluated or your function is evaluated at compile or at runtime. So this gives you even more flexibility and more ways to use functions at compile and runtime without having to duplicate the actual implementation. If you now look down to C, where I construct a global object of this bulb class and initialize it, so that would be my constant initialization. There is one more thing that C++20 added to the table. How can we make sure that my bulb object ceiling here actually gets initialized at compile time? We can make the ceiling object const_expr, but then we cannot change it at runtime anymore, which is something I really deeply want to do here. C++20's const init now comes into play. Const init means constant initialization, so initialization at compile time, but without adding the const to the object as const_expr would do. So here in C, I have an object that gets initialized at compile time, guaranteed. If that's not possible because somebody drops the const_expr from the constructor or passes something in that's no longer compile time friendly, then you get a compile time error. So once again, you have something you can build up towards the future. We can now make sure it gets initialized at compile time, and if something in your system changes and that would no longer be possible, you get a feedback. You can still decide that, all right, let's ignore the compile time thing, let's do it entirely at runtime, or you can fix your change and have still the compile time initialization going on. Okay, so this was added with C++20. So this is our bulb class. What else do we have? Oh yeah, we have the MAC address, right? So the 6 bytes, we usually represent them in some hexadecimal notation, depending on your operating system, separated by dashes or by colons. And we might start with a C string literal here, as for example in A. So I want to convert the C string literal MAC address string that we humans can read into the MAC address structure that I showed you before. And A here shows you a new element from C++20, the toArray function in the standard library. So you can pass it a string, and what you are getting back is an actual std_array with all the characters in the strings equal to the size of this std_array. So no more by hand doing that, and no more using a plain C array. You have a way to always get a very type-safe std_array back from these things. So that's my first step. I have now this data std_c_array object, and I have this function mech from string, which I use to convert this string here to the MAC address structure I showed you before. This is one way. This might also be the runtime case. Maybe I'm getting MAC addresses from user input, but maybe I also have some MAC addresses compiled into my binary. And so I might want to use a user-defined literal operator, as I show it in B, to directly convert a MAC address to the MAC address struct I showed you before. So these are basically my two options. Now here's my MAC from string function, and before we start looking into it, honestly, we are not really checking whether it's correct or not. I hope it is. But it's more about the parts it uses. So up there in A, so the very first thing is the return type of this function. And this is a new type from C++23 called std_expected. Please note the positive formulation here. So this is what we expect, the positive thing, because we expect that we get a return value back. And std_expected, you can compare it to a std_optional. It might have the return value or not. For std_optional, this is all the information you get. You either get a return value or you get the information that there is no return value there. My std_expected here takes a second parameter, except from the first one, which is the MAC address. The second one here, I picked std_error_c. So this is your type for the error condition. You could return a plain int here, or you can use the error code that's in the standard library. It's sufficient. You can provide your own class enum or regular enum if you want. And we basically look at an overlay. So either the return value is there or your error value is there. So in efficiency terms, we are talking about a union, and either the one or the other member is effective, but you're not storing both of them in the std_expected, only the larger one of them, so to speak. We are coming back to std_expected in a moment. The next thing we have in B here, if we go with the function signature, is the parameter I'm passing to MAC from string. This is C++20's std_span, and the std_span is a very small wrapper around a pointer. It stores the pointer and the length. So by that you have a, I would say, type-safe version of passing around, for example, a C array. A C array is the problem. If you look at POSIX API, you all the time pass a pointer and a length. And somebody has to create them, and somebody has to pass them around all the time. And if at some point you get confused and you pass the wrong pointer to the wrong length, or vice versa, you get an out-of-bounds error, or underflows, overflows, whatever. std_span's job is to take care of that and to say, hey, I'm constructible from a C-style array, I'm constructible from a std_array, I know the length, and I'm only compared to a std_array typed with one template parameter. This is the underlying type of your pointer, and the length I store in the runtime value. By that, you don't have the problem like with a std_array that your function now can only take a std_array of this particular size and type, of course, but the size is usually the problem. So your span is more flexible. So it's a real great addition to the standard library. One important notice here, we are not talking about a container, it's a view. A std_span only refers to your original data, so it doesn't ever copy the data, it just takes a pointer to your original data. Comes with several constructors. You also can construct it with a pointer length yourself if you're sure you're knowing what you're doing, and by that you can do it in only a few places. If we start looking down further in the converting function, Then you can see, I picked C, you can see it in all the early returns, the way I'm constructing the error value. I say I'm creating a std unexpected. Actually, it's a function that I'm calling which initializes my std expected with the unexpected value. The beauty of that is with this unexpected in your code, you can quickly spot the error path. So even if you're unfamiliar with the code, if your debugger stops there, you immediately know that's obviously in a condition that wasn't expected because it's unexpected. So for all my early returns, they are quite easy to spot. I think that's a great benefit here. And you're also having the option to have the strongly typed class enum here to be sure that you're only returning values in the error case that are really an error that's well known in the system. Below that, you can see in D, another thing I squeezed in, I like a lot. In C++17, we added from chars and as well to chars. So a way to convert from a C string to a number, to an integer, to floating point number, and vice versa. That was in C++17, but we needed a couple of more changes in further standards to, in C++23, finally make that function const expr. So this is why my entire mac from string here can be perfectly const expr in C++23. Std expected, std span, all the new types I showed you are const exprable, and my from chars also get promoted to being const expr in C++23. So one more function I now can run entirely at compile time. My user-defined literal operator here, I think you guessed it, right? It's a very small thing. It's the version that takes a const char star and the length, and internally I'm calling mac from string, and I'm using the opportunity to create a std span by passing the pointer and the length. And then after my mac from string returns, I'm directly calling .value. So for your std expected, you can call .value to get the value, you can call .error to get the error, and of course you have a function has value to check whether it has the value or the error condition. Whenever you are invoking the function for the, let's say, value that's not there, you're looking at an exception. So if you wanted to fetch the value but you have the error condition, you get an exception, and vice versa. So to summarize that, you basically should never plain access the value, because without knowing that the conversion worked in my case, you might hit an exception. So that's the one bad part about std expected. Which opens the question, what I'm doing here, because I'm blindly calling .value. And the reason lies a little bit up in the declaration of my user-defined literal operator. You see a C++20 element, const_eval. My user-defined literal operator is a const_eval function. That means this function runs only at compile time, never at runtime. So it has not the hybrid nature of a const expr function, it's only compile time. We also call it an intermediate function because basically it only exists in the compiler. So for my code here, that means if I'm calling .value at compile time, well, the compiler will terminate this compilation because I got an exceptions thrown, and this is the end of my compile time calculation. So this is why this code here is kind of safe. In C++20 and later, I would always recommend making your user-defined literal operators const_eval, because they are proxies to create objects and you always feed them with compile time data. So most of the times compilers get it right even without the const_eval, but it has a nice touch to it to help the compiler out here, and maybe even your colleagues to see what the goal here was when you created this function. All right, good so far. We have a couple of things. oh, there is this floating point stuff, right? So we need some way to convert a floating point number to its underlying bit representation. I'm not sure who of you ever dealt with the IEEE 754 format, so it's well defined. It starts with the sign bit, then we have the characteristics, which abstracts the exponent, and then we have the mantissa. Easily said, but how do I access the underlying representation? Most naive approach is, well, we receive the float, we know the float is 32-bit, and we know a uint32t has 32 bits. So we reinterpret cast the address of our float to a uint32t pointer, and we dereference that one, and by that accessing the underlying representation. Who has done that in the past? Oh, a few hands. You're a little shy, I guess. But thanks for admitting that. Yeah, me too. It might even work. The nice thing about undefined behavior is it can work. It can also break at any time. So this code here is undefined behavior, sadly. I get that from the name of the cast, we want to reinterpret something. It makes total sense, but standard-wise, this is not the operation that the reinterpret cast really supports. And it boils down to something we will see later again. It boils down to object lifetime. So the basic problem, among others, is that the source is a float, and we want to transfer that one to an int, but that int's constructor never got called, if you want to see it like that. So other approach that I saw in the wild, and if I ask this time, so it cannot be that most of this entire room never did one of the cases. So who used the union trick? So we have a float in there and a uint32t, we write the float, we read out the union. So who did that? More hands, all right. So maybe because you saw that one is free of undefined behavior. It's not. I'm not entirely sure whether it's even legal in C, but it's definitely undefined behavior in C++, because the lifetime rule kicks in. If you're writing the float and trying to read out the int, this int never became alive. This is the perfect way for the compiler to give you any value it wants. And that can be really fast for you and really cheap. Maybe not so cheap if your customers sue you because the code doesn't do what you want. But this trick doesn't work either. And honestly, before C++ 17, I think you had little chance of writing this piece of code correctly. We don't need to bother to look at the rest of this converting code. This line is the most crucial one. The rest you get right. And this is where C++ 20 now starts helping you out. We introduced a std_bit cast. And if you are in C++ 17, you can write this code using memcopy. Because in C++ 17, we started placing memcopy and memmove to be functions that can make an object become alive. Okay, and this is the crucial part for the standard and then for your compiler. You know, undefined behavior mostly kicks in if you're turning your optimizer level higher, because this is something the compiler can exploit then. And because the memcopy approach still takes some code, we added std_bit cast. Behind the scenes, it might do a memcopy, but basically the compiler can also know that and simply say, okay, I'm happy that now a uint32 object became alive with the bits that were previously stored in this floating point number. So here you have the undefined behavior free version. This is why there is the smiley, right? So this is the code you should write in C++ 20 and later. So this is something where C++ really gave you new opportunities to write correct code. Maybe even perfect code, but at least correct code. Nice. So improved that piece of code, made that one right. What else do we have? Oh yeah. What I want to show you here is not really what you might see on the first glance. So what this might look like is yet another way to solve the classic enum to string question. Because this is what it's doing. And if you're really interested in converting your enum to a string or vice versa, please, please, please upgrade to C++26 once we have it, because with static reflection, it's a piece of cake and it's really beautiful. This here is about something else. So obviously I have to write this enum to string function here. I have my color parts, red, green, and blue in the alpha level. And imagine that my system here has some kind of a user interface, so we want to represent these values to the user, and users should maybe know that the first value is red and the second one is green and not be confused. So we need some kind of getting a string out of that. And my getName function here, it takes such color parts enum. I store a std array inside that function that comes with the red, green, blue, and alpha strings. And then I'm using, at least I use add to access the element, so I'm bounce checked, but oh god. So the rest of this code is then a static cast to the type that I acquire with std_t from color parts applied to my index. Because since C++11, first of all, we can change the underlying type, and even before that, the compiler picked the underlying type based on different rules. So it was never, for sure, simply an integer. It could be a lot of things in between there. So the correct way to convert your enum to the underlying type is basically the static cast and fetching the underlying type with the help of the compiler. So we have two things in here. I have this const_std array together with the accessing the correct member of this array. I obviously tried with const_expr, so my entire function is const_expr, to have a const_expr friendly function here. The problem now is my data object, my data variable inside that block local function. Because it's a const_expr variable, if you take the const_expr conceptually away, it's just a const object on your call stack. The standard now guarantees you that if getName would be called recursively, each of your const variables inside your local scope has a unique address. So what that means is whenever you call getName here, despite that my variable itself, my object is const_expr, it needs to get initialized on the stack every time because every stack frame is a unique address. The right thing to do, if I want to do it like that, would be making that object static, because then it would live only once, it would be initialized only once. And if I want to initialize it at compile time, it would be right to make it static const_expr. Yet, before C++23, it was illegal to have a static const_expr variable in a const_expr function. This was solved in C++23. So now you can have a static const_expr variable inside your block local const_expr function. And with that, you have what you really wanted and need maybe for your embedded system. This data object now gets initialized at compile time. It lives only once. And because it gets initialized at compile time, because it's trivial, you don't even get any logs for it. And it's quite fast at runtime all the time. So this is the great addition here that you got in C++23. You had basically no way to do this before C++23. As I said, we want to send and receive data, right? So this is my receive function. We ignore the send part for today. We just want to receive. And you can see my receive function takes a std span of const unsigned int, char, sorry. You can see by that how much I like the std span here. This is my favorite data type when passing around arrays and bytes and so forth. Since my protocol luckily is so easy, I only have this one if in here that checks that the first byte of this byte stream I received is equal to my protocol update value, whatever that is. And if that's the case, I obviously received my light bulb control message, so I'm starting to process that. And now we are falling into something that we earlier already saw. We have a sequence of bytes, and we know that because the other side sent it to us, that this sequence of bytes is equal to a light bulb control structure. And we might also be right all the time about that. The tricky part is now convincing your compiler that the bytes are really a light bulb control structure. Again, naive approach is to say, well, I received these bytes, they're a pointer already, so let's cast them to a light bulb control pointer with a reinterpret cast, dereference that thing because our process function most likely here, which we will see in a minute, takes a reference to a light bulb control, and we are done. As the comment in A hints to you, this is undefined behavior. As it was before for the floating point trick, the light bulb control structure never came alive. And you have no way casting it in a sense that the compiler understands that this sequence of bytes now makes this light bulb control pointer carrying a real object. The only thing that you can do is the thing that I showed you previously, either with C++ 17 or 20 with the bit cast. You can cast the bits you received, the bytes, to a light bulb control structure. The drawback there is you have to cast it to the object. Your bit cast doesn't take pointers. It only takes objects. For some of you, that might already be okay. I most often worked in scenarios where zero copy was required. So I couldn't afford putting this light bulb control struct somewhere on the stack, copying all the bytes in there with a bit cast and then working with that one. I always wanted to use the raw bytes. Zero copy, you see that in kernels a lot or other network stacks. So while bitcast is an option, it's not really a feasible one here, for me at least. Luckily, C++ 23 introduced a new function in the standard library called start lifetime s. You can apply it here to a single data structure. You also have an array version which creates or makes an array of, for example, light bulb control structures become alive. This is your way to do this required action here in a sense of zero copy. So this is really, once again, asking the compiler to reinterpret the bits you received to a light bulb control. And that in a UB-free way, because the compiler understands now this became alive. You will find examples out there if you go to your favorite AI properly or your favorite old school search engine that show you how to implement that even before C++ 23. Build your own opinion about AI, but I can tell you they're all not working correctly under all circumstances. In the best case, you find a version that works for non-const data correctly, so that one is feasible to do, but I'm using here the const version, and that makes it way harder. So this is why we added that to the standard, because there is really no way for you to do this in a undefined behavior free way on const data. Okay, so even if you find examples, I wouldn't trust them. Only the non-const version, that's something that's doable. So this is something that C++ added, and I think it's something that's usually used in a close to embedded environment where we really receive bits and bytes and want to reinterpret them to something else. So this is my process function. As you could already guess, it takes a const reference light bulb control, and now it calls my global object ceiling, the light bulb, and updates the data. But here's another hurdle. Since we are talking about different devices, different architectures, we might run into that a little endian device sends something to us and we are a big endian device, or vice versa. Most of the times, when I worked in companies, we used the same notation as the rest of the world. So the network byte order is big endian. Some companies define it different. If they know that they only have little endian devices, they could talk little endian, and that's fine. But mostly whatever goes on the wire is big endian. So this is why I have the swap function in here. I need to swap the data when I receive them, depending on whether I'm a little or a big endian device. Assuming that the network byte order is big endian, so if I'm a little endian device, I have to switch the byte order. If I'm a big endian device, I can leave everything as it is. Perfect. So how does swap look like? So this is a macro-free and solely C++ based implementation, composed of C++ 17 and C++ 23. Sorry, not C++ 17, C++ 20 and 23. C++ 20 added a std_endian enum. That one comes with one enumeration called native, and that one carries whether it's little or big endian. Sorry for all the middle endian folks, nobody cares about that anymore. So it's either little or big endian, right? And we can compare that, and thanks to C++ 17's const exprif, we can figure out at compile time whether it's even possible that we are a little endian device and have to swap, or whether we are big endian, so trash that entire code and do not bloat my binary. And now in this const exprif, we have the C++ 23 edition. This is a std byte swap. So this is your C++ type-safe way of swapping the data types. You can use it with all the built-in types, and you can also technically extend it to your own data types if you need to do so. No longer using htons or htol and, well, applying it to the wrong sized data type, right? So this is perfect for embedded systems. At some point, we might run it to write configuration for our device to some kind of disk file system, or we want to read it. And whenever I do that, I prefer to use C++'s RAI approach, so resource acquisition is initialization, to have an automatic cleanup once I leave scope due to an error or the happy path reason. So I use my std unique pointer here. It's typed with a file pointer, so this is what I'm getting back from fopen. As you can see, I'm using my unique pointer with. And because my unique pointer is used to get a pointer and call delete on that pointer upon destruction, which isn't possible for a file, I provide a custom deleter. So this is the second parameter to my unique pointer. And there I'm saying, let's grab the signature from fclose. So this is my decal type. So this is the second parameter. It's a function pointer essentially. I can never recall whether fclose returns void or returns something else. So decal type it is. This works. My unique pointer, I can now create it with fopen. The drawback I have that I dislike is I now have to pass a second parameter to the constructor, the address of fclose. So first of all, I'm not happy from a usability point of view about this second pointer. The other thing is, if you ask me about efficiency, usually we say, well, use a unique pointer, it's just a tiny wrapper around a raw pointer, shouldn't notice any difference. At least if you're using it together with a custom deleter, you have to be careful, because if you look at this static assert here closely, I'm checking that the size of my unique pointers object is larger than the size of a void pointer. Precisely, it's the size of 2 pointers. Because my unique pointer now stores a pointer to the data and a pointer to the delete function. Reasonable. if you have a case where the delete function really would change during runtime, during different invocations. In my case, talking about fclose is there in the library. It comes with an address. I link against that thing and it never changes. So I really don't want to pay any overhead for something that's statically there and will never change. How can I optimize that? And this is a piece of code I really like. Might be because I came up with it. So I'm using a template alias here, a using alias. My template head here says I'm taking a type name t and using C++17's auto for my non-type template parameter, a delete fn. This is basically later a function pointer and at this point then the address of that function. My using alias, I name it unique pointer deleter. We can come up with a better name, I'm sure. And it points to a unique pointer of t. And the custom deleter here is the result of a decal type applied to a captureless lambda. So what are you looking at here is a C++20 edition that we can have captureless lambdas in so-called unevaluated contexts. So all this decal type does is grab you the class type of your lambda. Since it's captureless, it can never have any data members, so it doesn't have a constructor, it doesn't need any initialization. So it's ready to go as you write it. Why I'm doing that? Well, because I like lambdas, of course. There's another reason. The C++ standard, or the compilers, more precisely, they know an optimization technique that dates back way longer than C++11. And that's called the empty base class optimization, EBO. Whenever you have an empty class and you ask for the size of this class with a size of, the reply of your compiler is 1. Because an object in C++ must be addressable, and to be addressable, the size must be at least 1. So even for an empty class, if you ask, you get size of 1. If you don't ask, it's size of 0. This is something that a compiler now can exploit by saying, hey, if a class derives from an empty base class and the derived class comes with a size, there is no need to add size plus 1 for the empty base class, because you can ask for the size and the pointer of the derived class or the size of the derived class already represents something addressable. So an empty base class can be really 0. This is an optimization technique your compiler knows. It can do that if you somehow derive from this empty class. And as a simple mental model, assume that you have a unique pointer implementation where your implementation says, hey, if the custom deleter is a class, I'm deriving from that. Since if that class is empty, I don't add any overhead. And this is what happens here now. When I use my lambda, you could use an old custom class, but the lambda makes it really nice in one line. My lambda is captureless, so it's always an empty base class. And with that approach, you can see my static assert here now passes by saying, is the size of my unique pointer equal to the size of a single void pointer? So I just removed a lot of overhead that I added previously with the custom deleter. And this is also something I like, always stay efficient and only use the things that are really necessary here. So this is the, I think, great version that you can use to write this pattern. You also have now only one parameter to the unique pointer creation, because if it's strictly type for a file here with the fclose, there is no need to lock the address of fclose. We are creating that by saying my unique pointer deleter here is created by a file object and the delete function is fclose. And we are done. Question is, can we do better? Is there something that's still not optimal, where we might waste something? And now we are really looking at instructions. So let's say 1, 2, 3 instructions, they might be suboptimal here. We all are looking at a captureless lambda, right? And I showed you that in the past if you attended previous talks. A lambda is nothing more than a class with a call operator. And the next thing you know is a call operator is just a member function inside a class. More precisely, a non-static member function. And every non-static member function in C++ carries an implicit first parameter, the so-called dispointer. This, pun intended, is something that a compiler needs to prepare for you. Whenever you're calling a member function, whether this member function accesses any data, or in our case, never can access any data, or not, this implicit dispointer is there. So your compiler needs to prepare that dispointer and pass it around. And depending on the architecture and other things, it's in the range of 1 to 3 assembler instruction to prepare something that we all upfront know we never need. And we can never access, because there's nothing that can access that. C++23 gives you the option to optimize this case statically in the case your compiler fails to do so. So you can have a static lambda, and the static here donates to the call operator. I'm showing you the lambda version here because this is the new syntax for lambdas, but in C++23 you can make all call operators and array index operators static, and they behave like any other static member function, so it comes without the implicit dispointer. The consequence is that you also can no longer access any data inside that class that isn't static. This is some technique, as I said, to maybe save you up to 3 assembler instructions. So it's not a most, but sometimes we are really hunting for these things. Perfect. So I hope I could show you a few new tricks and a few things that C++ improved for use cases in embedded systems where you're looking for efficiency, for undefined behavior-free code, which is a real precious thing to have, or simply to have some tricks up in your sleeve to write more efficient code for your embedded device. We have time for questions left. At this point, I like to say I am Fertig. Thank you. Thank you.
Thank you, Andreas. We have a question. Our volunteers are having the mics. Okay, the first one.
In your last example, will the lambda be instantiated as a different class in different compilation units?
Thanks for giving me a slide back. You're asking whether the lambda in my decal type will be a new class in each TU. Yes. Yes.
So if you want to save on instruction size, then would a class be better than a lambda?
For instruction size.
So it's the same class in every compilation unit?
My simple answer will be yes. I imagine that the compiler, or more precisely the linker later, even with the lambda case, will figure out that it has 2 classes with just a different name, but exactly the same implementation, so you would not know if there's only one. So I assume that your linker will optimize this case away always. But if you want to be sure, as you said it, your own class will be the safe route. Yeah.
And I had written the exact same code as your process function that takes a span of constant sign char. Is there a reason it doesn't take stud byte in the span?
So you talk about
As the receive function, yes.
the receive function here, just to be precise. And you say why I'm not taking a stud byte. Honestly, simply because I didn't want to make things more complicated in here if people don't know stud byte or something like that. So I want to more relate to the audience, hopefully. I'm not sure if I succeeded.
So would it be a better fit for unstructured data that comes in from?
Would it be a better choice for unstructured data? Technically, from the standards points of view, as far as I know, all of them, so your unsigned car and your stud byte are more or less blessed with the same abilities. The only thing, or one reason to reach for stud byte would be that you have no operations that you can do on the stud byte. And this is one modeling option, right? On your unsigned car, you can do bit shifts and whatnot. You can add to it, you can subtract, which is maybe not what you want to express if you receive the byte or talking about a register. So stud byte can be better there. Yeah. You're welcome.
Okay, any more questions? Yeah, I see hands up, so let's go. Przepraszam, nie działa.
If it doesn't work, just try to shout your question and I repeat it. Oh, now it did, right? Yeah.
Do you know any embedded compilers that support C++ standards later than C++17?
So the question was whether I know
and
any...
with functional safety certification. This was the question.
So the full question was, do I know any embedded compiler that supports more than C++17 and comes with a certificate that says it supports functional safety?
Yeah, right.
I'm not the right person to ask about that. The latest contact I had with such a project, it was that the compiler only supported C++14. But that was a few years ago. So I'm not, landscaping the entire land there. So it might be. I simply don't know.
Okay, thanks. I know that newest IR compiler supports C++17. I don't know if in the fullest, but it supports C++17.
Yeah.
And thanks for the presentation. It was very great.
Thank you. You're welcome.
On the slide 21, the case with static lambda.
21. Oh, thank you. You remember the slide number? Yeah.
Okay, is the lambda necessary here at all? Because actually we do one call just to do yet another call, and despite the fact that maybe the compiler can simplify it, assuming that the delete function could be invocable, could we pass the delete function straightforwardly without wrapping it into a lambda?
Yeah, so you do C++, right? So you know there are hundreds of options to do the same thing. Yes, so one thing, if you want to stay generic, would be have a free function template that takes a T star and the delete fn and let that one use it.
Okay, so strictly, there is no particular reason that we need to wrap it in another lambda.
The main reason is having it being a class. So you don't need a lambda as your other entity asked. You can use your own class. Once you use a function, the unique pointer will store 2 pointers. One to the actual data, one to your delete function. So you don't have to be all fancy as I'm doing it here with the decal type and the lambda, but to be resource efficient, if you know that the address of your delete function never changes, if I understood your question correctly, then you need a class. You don't need a lambda, but you need a class at least.
Sure. Okay. Thank you.
You're welcome.
Okay, we are just on time, so maybe last question. I see a hand up here, so
With one in front.
one in front, and then of course Andreas is available. We can continue talking, but there will be a coffee break, and we are meeting at 4:30. So Andreas, one more last question. So let's go.
Yeah, I wanted to ask about if you know what's the cost of calling the at function, like because it will now throw if it's out of bound.
The add function, I had that.
Yeah, I'm familiar how exceptions are handled on x86 or like a bigger architectures, but I'm not sure how embedded usually calls it. I would expect some kind of std abort, but there's probably still some overhead generated, and I was wondering whether if it's not cheaper to basically bounce check manually or something like this. My question is, what's the footprint here of using the throwing version?
So I don't know exactly, because it depends on various factors what the footprint is. If you're talking about embedded, if you start looking in, for example, libstud C++ from GCC, they allow you to decide at compile time for the standard library what you want to do. Do you want to throw? Do you want to assert? Or whatever. So you have more option than simply letting add throw. So if you're worried about the memory footprint, one thing possible would be teach your standard library to assert instead of throwing. You can hook your own terminate handler. If you want to go down the road of throwing, you might look up one of the CPP-con talks by Khalil, I believe, forgot the last name, sorry. He had the talk last year and this year at CPP-con, making exceptions feasible in embedded systems by trimming the fat down real high. So that could be something. And other than that, it helps measuring. The reason why I wouldn't go against checking it yourself is because then for each add invocation you have to do that. And I can tell you from code reviews, I know people forget it, and I would be the first one. So this is why I would reach for add and try to configure your standard library. Another thing to add, last comment, C++26 will most likely give you a hardened standard library. So that means that you could, to some degree, pick there what they should do. So assert, throw, or whatsoever. But they will do that by default and even for the array index operator.
In the project I was part of, we were parsing the bytes at the very beginning, and then we were creating the type, and the type was only you can only create the type with the valid data. So whenever you pass the type already created, you can assume it's correct. So this is how we handled it, and I was wondering. And then you have only very cheap check at the very beginning, and you kind of check for integrity, like if the data even makes sense, not only the size, right?
Yeah, good approach.